Context Optical Compression. Haoran Wei, Yaofeng Sun, Yukun Li, DeepSeek-AI. Abstract. We present DeepSeek-OCR as an initial investigation into the feasibility of compressing long context via optical 2D mapping. DeepSeek-OCR consists of two components, DeepEncoder and DeepSeek3B-MoE-A570M as the decoder. Specifically, DeepEncoder serves as the core engine designed to maintain low activations under high-resolution input while achieving high compression ratios to ensure an optimal and manageable number of vision tokens. Experiments show that when the number of text tokens is within 10 times that of vision tokens, i.e. a compression ratio less than 10x, the model can achieve decoding OCR precision of 97%. Even at a compression ratio of 20x, the OCR accuracy still remains at about 60%. This shows considerable promise for research areas such as historical long context compression and memory forgetting mechanisms in LLMs. Beyond this, DeepSeek-OCR also demonstrates high practical value. On OmniDocBench, it surpasses OCR 2.0, 256 tokens per page, using only 100 vision tokens, and outperforms minor U 2.0, 6,000 plus tokens per page on average, while utilizing fewer than 800 vision tokens. In production, DeepSeek-OCR can generate training data for LLMs/VLMs at a scale of 200K plus pages per day, a single A140G. Codes and model weights are publicly accessible at http://github.com/DeepSeek-AI/DeepSeek-OCR. 600, 700, 700, 800, 800, 900, 900, 1000, 1000, 1100, 1100, 1200, 1200, 1300. Text tokens in per page. Ground truth, 0%, 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, 100%. Precision, 96.5%, 93.8%, 83.8%, 85.8%, 79.3%, 76.3%, 59.1%, 98.5%, 97.3%, 96.8%, 96.8%, 91.5%, 89.8%, 87.1%, 64.1%, 64 vistokes left, 100 vistokes left, 64 vistokes right, 100 vistokes right, 0x, 5x, 10x, 15x, 20x. Compression, 10.5, 6.7, 11.8, 7.5, 13.2, 8.5, 15.1, 9.7, 16.5, 10.6, 17.1, 11.3, 19.7, 12.6. A. Compression on Fox benchmark. 7,000, 6,000, 5,000, 4,000, 3,000, 2,000, 1,500, 0.1, 0.2, 0.3, 0.4, 0.5. Overall performance. Intern VL276B, Quen 2.5 VL7B, OLM-OCR, OCR Flux 3B. Intern VL378B, Quen 2.5 VL72B, Minor U 2.0, DeepSeek-OCR Gundam M200 DPI, DOTS-OCR, DOTS-OCR 200 DPI, Vision tokens greater than 1,500, average per image, more. Encoder series, DeepEncoder series, Quen encoder series, Intern VLMencoder series, other encoders, vision tokens less than 1,000, average vision tokens per image, fewer, high accuracy, ED less than 0.25, better, average vision tokens per image. B. Performance on OmniDocBench. Figure 1. Figure A shows the compression ratio, number of text tokens in ground truth, number of vision tokens model used, testing on Fox benchmark. Figure B shows performance comparisons on OmniDocBench. DeepSeek-OCR can achieve state-of-the-art performance among end-to-end models enjoying the fewest vision tokens. Contents. 1. Introduction. 3. 2. Related works. 4. 2.1. Typical vision encoders in VLMs. 4. 2.2. End-to-end OCR models. 4. 3. Methodology. 5. 3.1. Architecture. 5. 3.2 DeepEncoder. 5. 3.2.1 Architecture of DeepEncoder. 5. 3.2.2 Multiple Resolution Support. 6. 3.3 The MoE Decoder. 7. 3.4 Data Engine. 7. 3.4.1 OCR 1.0 Data. 7. 3.4.2 OCR 2.0 Data. 8. 3.4.3 General Vision Data. 9. 3.4.4 Text-only data. 9. 3.5 Training Pipelines. 9. 3.5.1 Training DeepEncoder. 10. 3.5.2 Training DeepSeek-OCR. 10. 4. Evaluation. 10. 4.1 Vision Text Compression Study. 10. 4.2 OCR Practical Performance. 12. 4.3 Qualitative Study. 12. 4.3.1 Deep Parsing. 12. 4.3.2 Multilingual Recognition. 16. 4.3.3 General Vision Understanding. 17. 5. Discussion. 18. 6. Conclusion. 19. Introduction. Current large language models, LLMs, face significant computational challenges when processing long textual content due to quadratic scaling with sequence length. We explore a potential solution leveraging visual modality as an efficient compression medium for textual information. A single image containing document text can represent rich information using substantially fewer tokens than the equivalent digital text, suggesting that optical compression through vision tokens could achieve much higher compression ratios. This insight motivates us to re-examine vision language models, VLMs, from an LLM-centric perspective, focusing on how vision encoders can enhance LLM's efficiency in processing textual information rather than basic VQA 12, 16, 24, 32, 41, what humans excel at. OCR tasks, as an intermediate modality bridging vision and language, provide an ideal testbed for this vision text compression paradigm, as they establish a natural compression-decompression mapping between vision and textual representations, while offering qualitative evaluation metrics. Accordingly, we present DeepSeek-OCR, a VLM designed as a preliminary proof of concept for efficient vision text compression. Our work makes 3 primary contributions. First, we provide comprehensive quantitative analysis of vision text token compression ratios. Our method achieves 96% plus OCR decoding precision at 9 to 10x text compression, circa 90% at 10 to 12x compression, and circa 60% at 20x compression on Fox 21 benchmarks, featuring diverse document layouts, with actual accuracy being even higher when accounting for formatting differences between output and ground truth, as shown in Figure 1A. The results demonstrate that compact language models can effectively learn to decode compressed visual representations, suggesting that larger LLMs could readily acquire similar capabilities through appropriate pre-training design. Second, we introduce DeepEncoder, a novel architecture that maintains low activation memory and minimal vision tokens even with high-resolution inputs. It serially connects window attention and global attention encoder components through a 16x convolutional compressor. This design ensures that the window attention component processes a large number of vision tokens, while the compressor reduces vision tokens before they enter the dense global attention component, achieving effective memory and token compression. Third, we develop DeepSeek-OCR based on DeepEncoder and DeepSeek3B-MoE-1920. As shown in Figure 1B, it achieves state-of-the-art performance with an end-to-end models on OmniDocBench while using the fewest vision tokens. Additionally, we equip the model with capabilities for parsing charts, chemical formulas, simple geometric figures, and natural images to enhance its practical utility further. In production, DeepSeek-OCR can generate 33 million pages of data per day for LLMs or VLMs using 20 nodes, each with 8 A140 GPUs. In summary, this work presents a preliminary exploration of using visual modality as an efficient compression medium for textual information processing in LLMs. Through DeepSeek-OCR, we demonstrate that vision text compression can achieve significant token reduction, 7 to 20x for different historical context stages, offering a promising direction for addressing long context challenges in large language models. Our quantitative analysis provides empirical guidelines for VLM token allocation optimization, while the proposed DeepEncoder architecture showcases practical feasibility with real-world deployment capabilities. Although focused on OCR as a proof of concept, this paradigm opens new possibilities for rethinking how vision and language modalities can be synergistically combined to enhance computational efficiency in large-scale text processing and agent systems. VIT, down, sample. VIT, LLM, down, sample, down, sample. Vary, DeepSeek VL. Unsupported pipeline parallel. 1024, 1024, 224, 224, 384, 384, 384, 384. Unsupported extreme resolution. Low native resolution. X overly small patches. Intern VL series, DeepSeek VL2. Usually greater than 15. X too many vision tokens. Quen 2.5, 3VL series. X too many vision tokens. X large activations. X small global view. X two pre-processes. X need long sequence length. W. H. Tokens equals W divided by 14 parentheses 16 times H divided by 14 parentheses 16. X slow inference speed. X hard to deployment. Figure 2. Typical vision encoders in popular VLMs. Here are 3 types of encoders commonly used in current open-source VLMs, all of which suffer from their respective deficiencies. 2. Related works. 2.1. Typical vision encoders in VLMs. Current open-source VLMs employ 3 main types of vision encoders, as illustrated in Figure 2. The first type is a dual-tower architecture, represented by Vary 36, which utilizes parallel SAM encoder to increase visual vocabulary parameters for high-resolution image processing. While offering controllable parameters and activation memory, this approach suffers from significant drawbacks. It requires dual image pre-processing that complicates deployment and makes encoder pipeline parallelism challenging during training. The second type is tile-based method, exemplified by Intern VL2.0, which processes images by dividing them into small tiles for parallel computation, reducing activation memory under high-resolution settings. Although capable of handling extremely high resolutions, this approach has notable limitations due to its typically low native encoder resolution below 512 by 512, causing large images to be excessively fragmented and resulting in numerous vision tokens. The third type is adapted resolution encoding, represented by Quen 2-VL35, which adopts the Navitat paradigm to directly process full images through patch-based segmentation without tile parallelization. While this encoder can handle diverse resolutions flexibly, it faces substantial challenges with large images due to massive activation memory consumption that can cause GPU memory overflow, and sequence packing requires extremely long sequence lengths during training. Long vision tokens will slow down both prefill and generation phases of inference. 2.2. End-to-end OCR models. OCR, particularly document parsing task, has been a highly active topic in the image-to-text domain. With the advancement of VLMs, a large number of end-to-end OCR models have emerged, fundamentally transforming the traditional pipeline architecture, which required separate detection and recognition expert models, by simplifying OCR systems. NuGet first employs end-to-end framework for academic paper OCR on arXiv, demonstrating the potential of models in handling dense persection tasks. GOAT OCR 2.0 expands the scope of OCR 2.0 to include more synthetic image parsing tasks and designs an OCR model with performance efficiency trade-offs, further highlighting the potential of end-to-end OCR researches. Additionally, general vision models such as Quen VL series, Intern VL series, and many their derivatives continuously enhance their document OCR capabilities to explore dense visual perception boundaries. However, a crucial research question that current models have not addressed is, for a document containing 1,000 words, how many vision tokens are at least needed for decoding? This question holds significant importance for research in the principle that a picture is worth 1,000 words. SAM, VidDet, 80M, Local Attention, Conv, 16x, Clip, Vit, 300M, Global Attention, Downsample, In by 16 by 16, Patches, Vision, Tokens, In by 16, DeepEncoder, DeepSeek3B-MoE-A570M, Prompt, Output, Decoder, Tokenizer, Embedding Layer, Input, Low Activation. Figure 3. The architecture of DeepSeek-OCR. DeepSeek-OCR consists of a DeepEncoder and a DeepSeek3B-MoE decoder. DeepEncoder is the core of DeepSeek-OCR, comprising 3 components: a SAM, 17, for perception dominated by window attention, a CLIP, 29, for knowledge with dense global attention, and a 16x token compressor that bridges between them. 3. Methodology. 3.1. Architecture. As shown in Figure 3, DeepSeek-OCR enjoys a unified end-to-end VLM architecture consisting of an encoder and a decoder. The encoder, namely DeepEncoder, is responsible for extracting image features and tokenizing, as well as compressing visual representations. The decoder is used for generating the required result based on image tokens and prompts. DeepEncoder is approximately 380M in parameters, mainly composed of an 80M SAM base 17 and a 300M clip large 29 connected in series. The decoder adopts a 3B-MoE architecture with 570M activated parameters. In the following paragraphs, we will delve into the model components, data engineering, and training skills. 3.2. DeepEncoder. To explore the feasibility of context optical compression, we need a vision encoder with the following features. 1. Capable of processing high resolutions. 2. Low activation at high resolutions. 3. Few vision tokens. 4. Support for multiple resolution inputs. 5. Moderate parameter count. However, as described in the section 2.1, current open-source encoders cannot fully satisfy all these conditions. Therefore, we design a novel vision encoder ourselves, named DeepEncoder. 3.2.1. Architecture of DeepEncoder. DeepEncoder mainly consists of 2 components: a visual perception feature extraction component dominated by window attention and a visual knowledge feature extraction component with dense global attention. To benefit from the pre-training gains of previous works, we use SAM base, patch size 16, and clip large as the main architectures for the 2 components respectively. For clip, we remove the first patch embedding layer since its input is no longer images but output tokens from the previous pipeline. Between the 2 components, we borrow from Vary and use a 2-layer convolutional module to perform 16x downsampling of vision tokens. Each convolutional layer has a kernel size of 3, stride of 2, padding of 1, and channels increase from 256 to 1024. Assuming we input 1024 by 1024 image, the DeepEncoder will segment it into 1024 by 16 by 1024 by 16 equals 4096 patch tokens. Since the first half of encoder is dominated by window attention and only 80M, the activation is acceptable. Before entering global attention, Figure 4. To test model performance under different compression ratios, requiring different numbers of vision tokens, and enhance the practicality of DeepSeek-OCR, we configure it with multiple resolution modes. The 4096 tokens go through the compression module, and the token count becomes 4096/16 equals 256, thus making the overall activation memory controllable. Table 1. Multi-resolution support of DeepEncoder. For both research and application purposes, we design DeepEncoder with diverse native resolution and dynamic resolution modes. Mode: native resolution, dynamic resolution, tiny, small, base, large, Gundam, Gundam M. Resolution: 512, 640, 1024, 1280, 640 plus 1024, 1280 plus 1280. Tokens: 64, 100, 256, 400, n times 10 plus 256, n times 256 plus 400. Process: resize, resize, padding, padding, resize plus padding, resize plus padding. 3.2. 2. Multiple resolution support. Suppose we have an image with 1,000 optical characters and we want to test how many vision tokens are needed for decoding. This requires the model to support a variable number of vision tokens. That is to say, the DeepEncoder needs to support multiple resolutions. We meet the requirement aforementioned through dynamic interpolation of positional encodings and design several resolution modes for simultaneous model training to achieve the capability of a single DeepSeek-OCR model supporting multiple resolutions. As shown in Figure 4, DeepEncoder mainly supports two major input modes, native resolution and dynamic resolution. Each of them contains multiple submodes. Native resolution supports 4 submodes: tiny, small, base, and large, with corresponding resolutions and token counts of 512 times 512, 64, 640 times 640, 100, 1024 times 1024, 256, and 1280 times 1280, 400. Since tiny and small modes have relatively small resolutions, to avoid wasting vision tokens, images are processed by directly resizing the original shape. For base and large modes, in order to preserve the original aspect ratio, images are padded to the corresponding size. After padding, the number of valid vision tokens is less than the actual number of vision tokens, with the calculation formula being n valid equals ceil n actual times 1 minus max w, h minus min w, h over max w, h, where w and h represent the width and height of the original input image. Dynamic resolution can be composed of two native resolutions. For example, Gundam mode consists of n times 640 times 640 tiles, local views, and a 1024 times 1024 global view. The tiling method following intern VL 2.0. Supporting dynamic resolution is mainly for application considerations, especially for ultra-high resolution inputs, such as newspaper images. Tiling is a form of secondary window attention that can effectively reduce activation memory further. It's worth noting that due to our relatively large native resolutions, images won't be fragmented too much under dynamic resolution. The number of tiles is controlled within the range of 2 to 9. The vision token number output by the DeepEncoder under Gundam mode is n times 100 plus 256, where n is the number of tiles. For images with both width and height smaller than 640, n is set to 0, i.e., Gundam mode will degrade to base mode. Gundam mode is trained together with the 4 native resolution modes to achieve the goal of one model supporting multiple resolutions. Note that Gundam Master Mode 1024 times 1024 local views plus 1280 times 1280 global view is obtained through continued training on a trained DeepSeek-OCR model. This is mainly for load balancing, as Gundam Master's resolution is too large and training it together would slow down the overall training speed. 3.3. The MoE decoder. Our decoder uses the DeepSeek-MoE 1920, specifically DeepSeek3B-MoE. During inference, the model activates 6 out of 64 routed experts and 2 shared experts, with about 570M activated parameters. The 3B DeepSeek-MoE is very suitable for domain-centric (OCR for us) VLM research, as it obtains the expressive capability of a 3B model while enjoying the inference efficiency of a 500M small model. The decoder reconstructs the original text representation from the compressed latent vision tokens of DeepEncoder as fdec rn dlatent to rn dtext x hat equals fdec of z, where n less than n, where z, rn, dlatent are the compressed latent vision tokens from DeepEncoder, and x hat, rn, dtext is the reconstructed text representation. The function fdec represents a nonlinear mapping that can be effectively learned by compact language models through OCR-style training. It is reasonable to conjecture that LLMs, through specialized pre-training optimization, would demonstrate more natural integration of such capabilities. 3.4. Data Engine. We constructed complex and diverse training data for DeepSeek-OCR, including OCR 1.0 data, which mainly consists of traditional OCR tasks such as Scene Image OCR and Document OCR. OCR 2.0 data, which mainly includes parsing tasks for complex artificial images such as common charts, chemical formulas, and plane geometry parsing data. General vision data, which is mainly used to inject certain general image understanding capabilities into DeepSeek-OCR and preserve the general vision interface. 3.4.1 OCR 1.0 data. Document data is the top priority for DeepSeek-OCR. We collect 30 million pages of diverse PDF data from the internet, with Chinese and English accounting for approximately 25 million and other languages accounting for 5 million. For this data, we create two types of ground truth: coarse annotations and fine annotations. Coarse annotations are A. Ground truth image. B. Fine annotations with layouts. Figure 5. OCR 1.0 Fine Annotations Display. We format the ground truth into an interleaved layout and text format, where each paragraph of text is preceded by the coordinates and label of it in the original image. All coordinates are normalized into 1000 bins. Directly from the full dataset using FITs, aimed at teaching the model to recognize optical text, especially in minority languages. Fine annotations include 2M pages each for Chinese and English, labeled using advanced layout models such as PP-Doc Layout 33, and OCR models such as Minuar RU 34 and GOT-OCR 2.0 38 to construct detection and recognition interleaved data. For minority languages, in the detection part, we find that the layout model enjoys certain generalization capabilities. In the recognition part, we use FITs to create small patch data to train a GOT-OCR 2.0, then use the trained model to label small patches after layout processing, employing a model flywheel to create 600K data samples. During the training of DeepSeek-OCR, coarse labels and fine labels are distinguished using different prompts. The ground truth for fine annotation image-text pairs can be seen in Figure 5. We also collect 3M word data, constructing high-quality image-text pairs without layout by directly extracting content. This data mainly brings benefits to formulas and HTML formatted tables. Additionally, we select some open-source data, 28, 37, as supplements. For natural scene OCR, our model mainly supports Chinese and English. The image data sources come from LA-ION 31 and Wukong 13, labeled using Paddle OCR 9, with 10M data samples each for Chinese and English. Like Document OCR, Natural Scene OCR can also control whether to output detection boxes through prompts. 3.4.2 OCR 2.0 data. Following GOT-OCR 2.0 38, we refer to chart, chemical formula, and plane geometry parsing data as OCR 2.0 data. For chart data, following one chart 7, we use pie charts and matplotlib. A. Image text ground truth of chart. B. Image text ground truth of geometry. Figure 6. For charts, we do not use one charts and dictionary format, but instead use HTML table format as labels, which can save a certain amount of tokens. For plane geometry, we convert the ground truth to dictionary format, where the dictionary contains keys such as line segments, endpoint coordinates, line segment types, etc., for better readability. Each line segment is encoded using the slow perception 39 manner. To render 10M images, mainly including commonly used line, bar, pie, and composite charts. We define chart parsing as image to HTML table conversion task as shown in Figure 6a. For chemical formulas, we utilize SMIL's format from PubChem as the data source and render them into images using RDKit, constructing 5M image text pairs. For plane geometry images, we follow slow perception 39 for generation. Specifically, we use perception ruler size as 4 to model each line segment. To increase the diversity of rendered data, we introduce geometric translation invariant data augmentation, where the same geometric image is translated in the original image corresponding to the same ground truth drawn at the centered position in the coordinate system. Based on this, we construct a total of 1M plane geometry parsing data, as illustrated in Figure 6b. 3.4.3 General Vision Data. DeepEncoder can benefit from CLIP's pre-training gains and has sufficient parameters to incorporate general visual knowledge. Therefore, we also prepare some corresponding data for DeepSeek-OCR. Following DeepSeek VL2 40, we generate relevant data for tasks such as caption, detection, and grounding. Note that DeepSeek-OCR is not a general VLM model, and this portion of data accounts for only 20% of the total data. We introduce such type of data mainly to preserve the general vision interface so that researchers interested in our model and general vision task can conveniently advance their work in the future. 3.4.4 Text-only data. To ensure the model's language capabilities, we introduced 10% of in-house text-only pre-trained data, with all data processed to a length of 8192 tokens, which is also the sequence length for DeepSeek-OCR. In summary, when training DeepSeek-OCR, OCR data accounts for 70%, general vision data accounts for 20%, and text-only data accounts for 10%. 3.5 Training pipelines. Our training pipeline is very simple and consists mainly of two stages. A. Training DeepEncoder independently. B. Training the DeepSeek-OCR. Note that the Gonda master mode is obtained by continuing training on a pre-trained DeepSeek-OCR model with 6M sample data. Since the training protocol is identical to other modes, we omit the detailed description hereafter. 3.5.1 Training DeepEncoder. Following Very 36, we utilize a compact language model 15 and use the next token prediction framework to train DeepEncoder. In this stage, we use all OCR 1.0 and 2.0 data aforementioned, as well as 100M general data sampled from the Leon 31 dataset. All data is trained for 2 epochs with a batch size of 1,280. Using the Atom W23 with cosine annealing scheduler 22 and a learning rate of 5E5. The training sequence length is 4096. 3.5.2 Training DeepSeek-OCR. After DeepEncoder is ready, we use data mentioned in section 3.4 to train the DeepSeek-OCR, with the entire training process conducted on the high LLM platform. The entire model uses pipeline parallelism, PP, and is divided into 4 parts, with DeepEncoder taking 2 parts and the decoder taking 2 parts. For DeepEncoder, we treat SAM and the compressor as the vision tokenizer, place them in PP0, and freeze their parameters, while treating the clip part as input embedding layer and place it in PP1 with unfrozen weights for training. For the language model part, since DeepSeek3B-MoE has 12 layers, we place 6 layers each on PP2 and PP3. We use 20 nodes, each with 8 A140 GPUs, for training, with a data parallelism of 40 and a global batch size of 640. We use the Atom W optimizer with a step-based scheduler and an initial learning rate of 3E5. For text-only data, the training speed is 90 B tokens per day, while for multimodal data, the training speed is 70 B tokens per day. Table 2. We test DeepSeek-OCR's vision-text compression ratio using all English documents with 600 to 1300 tokens from the Fox benchmarks. Text tokens represent the number of tokens after tokenizing the ground truth text using DeepSeek-OCR's tokenizer. Vision tokens 64 or 100 respectively represent the number of vision tokens output by DeepEncoder after resizing input images to 512 and 640 by 640. Text tokens, vision tokens 64, vision tokens 100, precision, compression, pages, 600 to 700, 96.5%, 10.5x, 98.5%, 6.7x, 700 to 800, 93.8%, 11.8, 97.3%, 7.5, 28, 800 to 900, 83.8%, 13.2, 96.8%, 8.5, 28, 900 to 1000, 85.9%, 15.1, 96.8%, 9.7, 14, 1000 to 1100, 79.3%, 16.5, 91.5%, 10.6, 11, 1100 to 1200, 76.4%, 17.7, 98.8%, 11, 1200 to 1300, 59.1%, 19.7, 87.1%, 12.6, 4. Evaluation. 4.1. Vision Text Compression Study. We select Fox 21 benchmarks to verify DeepSeek-OCR's compression-decompression capability for text-rich documents. In order to preliminarily explore the feasibility and boundaries of context optical compression, we use the English document portion of Fox, tokenize the ground truth text with DeepSeek-OCR's tokenizer, vocabulary size of approximately 129K, and select documents with 600 to 1300 tokens for testing, which happens to be 100 pages. Since the number of text tokens is not large, we only need to test performance in tiny and small mode, where tiny mode corresponds to 64 tokens and small mode corresponds to 100 tokens. We use the prompt. Table 3. We use OmniDocBench 27 to test the performance of DeepSeek-OCR on real document parsing tasks. All metrics in the table are edit distances, where smaller values indicate better performance. Tokens represents the average number of vision tokens used per page, and 200 dpi means using fits to interpolate the original image to 200 dpi. For the DeepSeek-OCR model, the values in parentheses in the tokens column represent valid vision tokens calculated according to equation 1. Model. Tokens. English, Chinese. Overall text, formula, table, order. Overall text, formula, table, order. Pipeline models. Dolphin, 11, minus 0.356, 0.352, 0.465, 0.258, 0.35, 4.4, 4.4, 6.04, 3.51, 3.51. Marker, 1, minus 0.296, 0.08, 3.74, 0.6, 11, 4.97, 3.29, 6.88, 6.78, 3.39. Math picks, 2, minus 0.191, 0.105, 3.60, 3.24, 10, 4.31, 381, 454, 320, 3.30. Minor U 2.1.1, 34, minus 0.162, 0.07, 3.13, 0.16, 19, 244, 111, 581, 15, 136. Monkey OCR 1.2b, 18, minus 0.154, 0.06, 3.25, 0.16, 19, 263, 179, 464, 168, 243. PP structure V3, 9, minus 0.152, 0.73, 3.25, 0.16, 17, 223, 136, 535, 111. End-to-end models. Nougat, 6, 2352, 0.452, 0.365, 0.488, 0.572, 0.382, 1.973, 1.998, 1.941, 1.00, 1.954. Small duckling, 25, 392, 0.493, 0.262, 0.753, 0.729, 0.227, 0.816, 0.838, 0.997, 0.907, 0.522. Intern VL2 76, 6790, 0.44, 0.353, 0.543, 0.547, 0.317, 0.443, 0.29, 0.701, 0.555, 0.228. Quen 2.5 VL7 3949, 0.316, 0.151, 376, 0.598, 0.138, 399, 324, 0.50, 627, 0.226. OLM-OCR 3949, 0.326, 0.097, 455, 608, 15, 469, 323, 655, 652, 0.277. GOT OCR 2.0, 256, minus 0.287, 189, 360, 459, 14, 141, 315, 528, 520, 0.28. OCR Flux 3B 3949, 0.238, 112, 447, 269, 126, 349, 325, 716, 162, 263. GPT-4o minus 0.233, 144, 425, 234, 128, 399, 409, 606, 329, 0.251. Intern VL378B 6790, 0.218, 117, 38, 329, 109, 306, 210, 533, 0.282, 0.161. Quen 2.5 VL72 3949, 0.214, 0.092, 315, 341, 106, 261, 180, 434, 262, 0.168. DOTS OCR 3949, 0.182, 137, 320, 166, 182, 261, 229, 570, 116, 261. Gemini 2.5 Pro minus 0.14, 055, 365, 13, 049, 212, 168, 439, 119, 112. Minor U 2.0 6790, 0.133, 0.045, 327, 150, 0.066, 238, 115, 506, 0.209, 0.122. DOTS OCR 200 DPI 30, 5545, 0.125, 0.032, 329, 109, 0.04, 160, 0.06, 506, 0.092, 0.067. DeepSeek-OCR end-to-end, tiny, 60, 0.386, 373, 469, 422, 328, 361, 307, 635. Tiny, 100, 0.221, 142, 373, 242, 112, 284, 240, 530, 159, 205. Small, 100, 0.221, 142, 373, 242, 112, 284, 204, 530, 159, 205. Base, 100, 0.221, 142, 373, 242, 112, 284, 204, 530, 159, 205. Large, 100, 0.221, 142, 373, 242, 112, 284, 204, 530, 159, 205. Gundam, 100, 0.221, 142, 373, 242, 112, 284, 204, 530, 159, 205. Gundam, 100, 0.221, 142, 373, 242, 112, 284, 204, 530, 159, 205. Without layout. Context. Image. Free. OCR. As shown in Table 2, within a 10x compression ratio, the model's decoding precision can reach approximately 97%, which is a very promising result. In the future, it may be possible to achieve nearly 10x lossless context compression through text-to-image approaches. When the compression ratio exceeds 10x, performance begins to decline, which may have two reasons. One is that the layout of long documents becomes more complex, and another reason may be that long texts become blurred at 512 by 512 or 640 by 640 resolution. The first issue can be solved by rendering text onto a single layout page, while we believe the second issue will become a feature of the forgetting mechanism. When compressing tokens by nearly 20x, we find that precision can still approach 60%. These results indicate that optical context compression is a very promising and worthwhile research direction, and this approach does not bring any overhead because it can leverage VLM infrastructure, as multimodal systems inherently require an additional vision encoder. Table 4. Edit distances for different categories of documents in OmniDocBench. The results show that some types of documents can achieve good performance with just 64 or 100 vision tokens, while others require Gundam mode. Mode. Type. Book, slides, financial report, textbook, exam paper, magazine, academic papers, notes, newspaper, overall. Tiny. 0.147, 0.116, 0.207, 0.173, 0.294, 0.201, 0.395, 0.297, 9.4, 0.32. Small. 0.085, 0.11, 0.079, 0.147, 0.171, 0.107, 0.131, 0.187, 7.44, 0.205. Base. 0.37, 0.08, 0.027, 0.1, 0.13, 0.07, 0.05, 0.176, 6.45, 0.156. Large. 0.38, 0.108, 0.02, 0.08, 0.109, 0.06, 0.05, 0.155, 3.35, 0.11. Gundam. 0.35, 0.85, 0.289, 0.09, 0.94, 0.59, 0.39, 0.153, 1.22, 0.83. Gundam M. 0.52, 0.09, 0.34, 0.10, 0.07, 0.09, 0.04, 0.10, 0.99, 0.77. 4.2. OCR Practical Performance. DeepSeek-OCR is not only an experimental model, it has strong practical capabilities and can construct data for LLM/VLM pre-training. To quantify OCR performance, we test DeepSeek-OCR on OmniDocBench with results shown in Table 3. Requiring only 100 vision tokens, 640 by 640 resolution, DeepSeek-OCR surpasses GOT-OCR 2.0, which uses 256 tokens. With 400 tokens, 285 valid tokens, 1280 by 1280 resolution, it achieves on-par performance with state-of-the-arts on this benchmark. Using fewer than 800 tokens, Gundam mode, DeepSeek-OCR outperforms Minor U 2.0, which needs nearly 7,000 vision tokens. These results demonstrate that our DeepSeek-OCR model is powerful in practical applications, and because the higher tokens compression, it enjoys a higher research ceiling. As shown in Table 4, some categories of documents require very few tokens to achieve satisfactory performance, such as slides, which only need 64 vision tokens. For book and report documents, DeepSeek-OCR can achieve good performance with only 100 vision tokens. Combined with the analysis from Section 4.1, this may be because most text tokens in these document categories are within 1,000, meaning the vision token compression ratio does not exceed 10x. For newspapers, Gundam or even Gundam Master Mode is required to achieve acceptable edit distances because the text tokens in newspapers are 4 to 5,000, far exceeding the 10x compression of other modes. These experimental results further demonstrate the boundaries of context optical compression, which may provide effective references for researchers on the vision token optimization in VLMs and context compression for getting mechanisms in LLMs. 4.3. Qualitative Study. 4.3.1. Deep Parsing. DeepSeek-OCR possesses both layout and OCR 2.0 capabilities, enabling it to further parse images within documents through secondary model calls, a feature we refer to as deep parsing. As shown in Figure 7, 8, 9, 10, our model can perform deep parsing on charts, geometry, chemical formulas, and even natural images, requiring only a unified prompt. Convert the document to Markdown. In the field of financial research reports, the deep parsing mode of DeepSeek-OCR can be used to obtain structured results of charts within documents. Charts are a crucial form of data representation in finance and scientific fields, and the chart structured extraction is an indispensable capability for future OCR models. Figure 8. For books and articles, the deep parsing mode can output dense captions for natural images in the documents. With just a prompt, the model can automatically identify what type of image it is and output the required results. The image depicts an indoor classroom setting with a group of children and an adult. The children are seated on the floor, facing a woman who is standing and appears to be reading or presenting to them. The woman is wearing a brown sweater and blue jeans. The children are dressed in various colors, with some wearing short pants and others in long pants. The classroom has a green wall with educational posters and a bulletin board. The floor is covered with a gray carpet. To the left, there is a wooden dresser with a drawer partially open, and a chair is visible behind it. On the right side of the image, there is a purple beanbag chair. The children are engaged with the woman, with some looking at her and others looking down or away. The room is well lit, and the overall atmosphere seems to be one of attentiveness and learning. The text Biblioteca is visible on the wall, suggesting that the room may be part of a library or a section dedicated to books. The presence of educational materials and the organized layout of the room indicate that this is a space designed for learning and reading. Figure 9. DeepSeek-OCR and deep parsing mode can also recognize chemical formulas within chemical documents. In the future, OCR 1.0 plus 2.0 technology may play a significant role in the development of VLM, LLM in STEM fields. Deep parse the figure. DeepSeek-OCR also possesses the capability to copy, structure simple planar geometric figures. Due to the intricate interdependencies among line segments and geometric shapes, parsing geometry task is extremely challenging and has a long way to go. 4.3.2. Multilingual recognition. PDF data on the Internet contains not only Chinese and English, but also a large amount of multilingual data, which is also crucial when training LLMs. For PDF documents, DeepSeek-OCR can handle nearly 100 languages. Like Chinese and English documents, multilingual data also supports both layout and non-layout OCR formats. The visualization results are shown in Figure 11, where we select Arabic and Sinhala languages to demonstrate results. Free OCR. Convert the document to Markdown. Figure 11. To endow the capability of processing widely crawled PDFs, multilingual data, we train our model with OCR capabilities for nearly 100 languages. Minority language documents can also support both layout and non-layout outputs through different prompts. 4.3.3 General Vision Understanding. We also provide DeepSeek-OCR with a certain degree of general image understanding capability. Locate 11-2 in the image. A green plastic container labeled for food storage purposes. The lid is yellow and appears slightly worn out. On the front label, at the top left corner, some Chinese characters. In bold black letters near the center top reads 6月香, June fragrance. Below that, smaller white font states 鲜甜咸香, which translates roughly to fresh, sweet, salty, fragrant. Dominating the middle part of the label is large lettering stating 豆瓣酱, meaning bean paste sauce. Additional information includes a small circular logo indicating quality assurance, 优质品, an illustration showing what seems like a dish made using bean paste sauce. Text below the main title says 专注25年, 只做圆圆酱, translating to focusing since 1998, only making authentic fermented bean paste. On the bottom right side, additional product specifications include 净含量500 gram. Overall style or type, it looks like commercial packaging designed specifically for preserving food items within the jar. It has clear labeling intended for easy identification and understanding among consumers who read Mandarin. Note, there might be slight variations due to handwriting styles, but overall maintains readability regarding brand identity and contents description. Locate the teacher in the image. 这是一张照片，展示了一辆红色的消防栓。消防栓上有一个笑脸，显得非常友好和亲切。消防栓的顶部有一个黑色的盖子，周围有一些金属铆钉。在消防栓的底部有一个粉红色的贴纸，上面写着 bow tie。背景中可以看到一条街道，街道上有几辆停放的汽车和一些树木。整体画面给人一种温馨和友好的感觉。Filter out all objects in the image. Time. Just happened. Crystal clear. 1 hour. Very clear. Clear. 1 day. 1 week. 1 month. 1 year. Blurry. Very blurry. Almost gone. Distance. 10 centimeter. Crystal clear. 50 centimeter. Very clear. Clear. 1 meter. 3 meters. 10 meters. 20 meters. Blurry. Very blurry. Almost gone. Resolution. Crystal clear. Gundam. Very clear. Clear. Large. Base. Small. Tiny. Blurry. Very blurry. Almost gone. Text token. Memory. Vision. Text. Figure 13. Forgetting mechanisms constitute one of the most fundamental characteristics of human memory. The context's optical compression approach can simulate this mechanism by rendering previous rounds of historical text onto images for initial compression, then progressively resizing older images to achieve multi-level compression, where token counts gradually decrease and text becomes increasingly blurred, thereby accomplishing textual forgetting. For older contexts, we could progressively downsizing the rendered images to further reduce token consumption. This assumption draws inspiration from the natural parallel between human memory decay over time and visual perception degradation over spatial distance. Both exhibit similar patterns of progressive information loss, as shown in Figure 13. By combining these mechanisms, Context's optical compression method enables a form of memory decay that mirrors biological forgetting curves, where recent information maintains high fidelity, while distant memories naturally fade through increased compression ratios. While our initial exploration shows potential for scalable ultra-long context processing, where recent contexts preserve high resolution and older contexts consume fewer resources, we acknowledge this is early-stage work that requires further investigation. The approach suggests a path toward theoretically unlimited context architectures that balance information retention with computational constraints, though the practical implications and limitations of such vision text compression systems warrant deeper study in future research. 6. Conclusion. In this technical report, we propose DeepSeek-OCR and preliminarily validate the feasibility of context optical compression through this model, demonstrating that the model can effectively decode text tokens exceeding 10 times the quantity from a small number of vision tokens. We believe this finding will facilitate the development of VLMs and LLMs in the future. Additionally, DeepSeek-OCR is a highly practical model capable of large-scale pre-training data production, serving as an indispensable assistant for LLMs. Of course, OCR alone is insufficient to fully validate true context optical compression, and we will conduct digital optical text interleaved pre-training, needle in a haystack testing, and other evaluations in the future. From another perspective, optical context compression still offers substantial room for research and improvement, representing a promising new direction. References. 1. Marker. URL http://github.to/marker. 2. MathPix. URL http://mathpix.com. 3. OCR Flux 2025. URL http://github.chatdoc.com/OCRFlux. 4. GAI Gemini 2.5 2025. URL http://gemini.google.com. 5. SBY K Chen X Lu J1 WG S Song K Dang P1 S1 J Tang H Zong Y Zhu M Yang Z Li J1 P1 W Ding ZF YX J Ye X Zhang T Shi Z Cheng H Zong Z Yang HX and J Lin. QN2.5 Technical Report. RxRV Preprint RxRV 2502.1392 2025. 6. L. Blecher, G. Kukarul, T. Skalom, and R. Stojnik. NuGet, Neural Optical Understanding for Academic Documents. RxRV Preprint RxRV 2308.1348 2023. 7. J. Chen, L. Kong, H. Wei, C. Liu, Z. Gay, L. Zhao, J. Sun, C. Han, and X. Zhang. OneChart. Purify the chart structural extraction via one auxiliary token. In proceedings of the 32nd ACM International Conference on Multimedia. Pages 147 to 155, 2024. Zichen, W. Wang, H. Tian, S. Yi, Z. Gao, E. Kui, W. Tung, K. Hu, J. Lo, Z. Ma, et al. How far are we to GPT-4V? Closing the gap to commercial multimodal models with open source suites. RxRV Preprint RxRV 2404.1682, 2024. 9. C. Cui, T. Sun, M. Lin, T. Gao, Y. Zhang, J. Liu, X. Wang, Z. Zhang, C. Zhou, H. Liu, et al. Paddle OCR 3.0 Technical Report. RxRV, preprint, RxRV 2507.5595, 2025. 10. M. Dahani, J. Jalonga, B. Mustafa, P. Padlevsky, J. Heek, J. Gilmer, A. Steiner, M. Karan, R. Gayhos, I. Al-Dabdel-Mohisin, et al. Patch and Pack, Navit, a vision transformer for any aspect ratio and resolution. Advances in Neural Information Processing, 36, 3632 to 3656, 2023. 11. H. Feng, S. Wei, X. Fei, W. Shi, Y. Han, L. Liu, J. Liu, B. Wu, Q. Liu, C. Lin, et al. Dolphin, document image parsing via heterogeneous anchor prompting. RxRV, preprint, RxRV 2505.1405, 2025. 12. Y. Goyal, T. Kott, D. Summerstay, D. Batra, and D. Parekh, making the V in VPUA matter, elevating the role of image understanding in visual question answering. In Proceedings of the ICCC Conference on Computer Vision and Pattern Recognition, pages 6904 to 6913, 2017. 13. J. Gu, X. Meng, G. Liu, L. Ho, N. Minzhou, X. Liang, L. Yao, R. Han, W. G, X. Zhang, et al. Wukong, a 100 million large-scale Chinese cross-modal pre-training benchmark. Advances in Neural Information Processing, 35, 26481 to 26431, 2022. 14. Highflyer, HAI-LLM, efficient and lightweight training tool for large models, 2023. URL http://website.highflyer.com. 15. S. Iyer, X. V. Lin, R. Pasunaru, T. Mihailov, D. Simig, P. U. K. Shuster, T. 1, Q. Liu, P. S. Cora, et al. Opt-ILL, Scaling Language Model Instruction Meta-Learning Through the Lens of Generalization. RxRV, preprint, RxRV 2012.1207, 2022. 16. S. Kazimzada, V. Ardonas, M. Matin, and T. Berg. Refer It Game, referring to objects in photographs of natural scenes. In Proceedings of the 2014 Conference on Empirical Methods in Natural Language Processing, pages 787 to 798, 2014.